Next question. Problem number 2 is the centrifuge. Okay, so does the mass of the person matter in terms of how fast you spin this? Okay, so you got a kid coming in. A kid is about 90 pounds. And now all of a sudden you got this linebacker, which is about 350 pounds. So what do? You want everyone to enjoy this experience, right? So would you just throttle it up? Do you max out the speed? So what's going on? So do you change the speed depending upon the heaviest person that you need to accommodate? Or the same speed is going to work for everyone? Okay, so what do you guys think? All right, so the speed with which you will spin this is going to change from person to person. So what is the minimum required speed, which is going to accommodate just about everyone? All right, so problem number 2, this is going to be a rotor. Notice that you have a 100-pound kid, and then you have a 400-pound adult. Okay, so the radius is going to be 15 feet. So estimated coefficient of friction of the surface is going to be 0.33. Okay, so depending on depending upon the slipperiest, I'm just making thing up right now, of the outfit that you could wear. So what is the minimum required speed so that each and every single person will become suspended on the wall? Okay, so Isla says it's going to be the same speed for everyone. Sophia says the same. Sophia says the same thing. So give yourselves 5 points, guys. Most of you guys would think that the heavier the person is, the larger the speed is going to be, right? Required, so that the person does not slip. That's one way of looking at it. That's what the majority of you guys usually think. All right, so let's check to see if there's any validity to that kind of thinking. All right, so this is problem number 2. So this is the problem that we'll focus on. So let's go back, get out of it, go to the worksheet. Oh my God. All right, this is not the right worksheet. All right, so I'm going to draw this out and then identify the forces before I move forward. All right, so this thing is going to be spinning on its axis in this direction. All right, so the question is, what is the minimum required speed in terms of meters per second to miles per hour? And I'll place the person right here on the wall. And then I'm going to place my X and Y coordinate system right here. All right, so X coordinate system, the Y coordinate system. And really, I don't need an X coordinate system. I need a radial coordinate system. So, boom, get rid of that. I need a radial coordinate system pointing towards, this is my radial coordinate system. R is the radial coordinate system. So it's pointing towards the center of the circle. Identify my forces. All right, this thing is going to have weight in this direction. That was cute. All right, so this is the weight. And the reason why the person is not slipping because of the frictional force is this static frictional force. All right, at the minimum required speed, the static frictional force is going to be maximized, which means that the person is at the verge of skidding at that point. So let's just get this up so that they have the same value. And there's going to be a radial force pointing towards the center of the circle, so that's the normal force. All right, so I identify all my forces. So what is the minimum required speed for this person to be suspended on the wall? All right, so I can get the minimum required speed. And before I do that, then we get the coefficient of static friction. It's going to be 0.33. I have a small mass, 100 pounds. And then we have a larger mass. This guy's going to be, what is it, 400 pounds? Okay, so we got 2 masses. All right, so will the speed depend on the mass? That's what we will figure out. All right, so I'm going to be going after the speed, and this is circular motion. And then I know I can get the speed from circular motion. All right, so here's what I know. I know that the centrifugal force is the same as the normal force. And I also know that the centrifugal force has a generic formula, which has speed in it. All right, so R is the radius. I think the R is given, so the R is right here. All right, so we got an expression for R. All right, so that's 15 feet. So somebody needs to convert 15 feet to meters. So we got to use that. All right, so back substitution. MV squared divided by R equals N. All right, so solve for V at this point because that's what I'm looking for. All right, so I'm going to get rid of the mass. And also I'm going to get rid of R. So you have N times R divided by M. Okay, those of you guys who came up with the numbers, give yourselves 5 points. All right. Get rid of the square by taking the square root of both sides. All right, so what do we have? We got V. It's going to be N times R divided by M under the square root. Okay, so if we stop at this point, kind of get an answer. Let's check to see if the answer makes sense. Okay, so regarding how fast we need to spin this. Okay, notice that the bigger the mass is, smaller the speed is going to be for this person to become suspended. Okay, and that kind of makes sense because bigger the mass is, bigger your tendency to go in a straight line at a constant speed, right? So, which means that the heavier person is going to require a smaller speed to become suspended on the wall. But does that make sense? Because initially you thought that, hey, if the person is heavy, you kind of want to throttle this up, right? You want to go faster so that this person is not slipping down. And all of a sudden you do a little bit of algebra, you realize that the mass is in the denominator, so the mass is right here. So bigger mass is going to require a lower speed. And then physics kind of allows you to be able to justify that. But is that the correct justification? No, because when you actually look at the numbers, all of a sudden you realize that you got an expression for mass, small or big, so you can use it for either way, which means that you're going to end up getting 2 different speeds. You get the same radius for both of them, but N is a reaction force, guys. Where do you get the N from? You get the N from the surface. Heavier you are, the larger the N is going to be because you're going to be pressed against the surface harder because your body wants to keep on moving in a straight line at a constant speed, so it's going to end up generating a much larger reaction force. All right, smaller the person is, smaller the mass is, the smaller the N is going to be because the smaller mass does not have, it's going to have a smaller tendency to go to retain that motion in a straight line at a constant speed. And N is a reaction force to your mass and not to your weight, but your mass, because your mass is the measure of inertia. Bigger the mass is, the bigger the tendency to go in a straight line at a constant speed. So, which means that this N is going to be sensitive to W. So you kind of expect that. So does this mean that the mass is not going to matter? So at this point, we will have to do a little bit of algebra. So which means that we need to focus on N at this point. So N is what we need. All right, so get out of here. All right, so speaking of N, we're going to be interested in N at this point. All right, so this person is going to be pressed against the surface. And N is going to be a force in this direction. And this person has weight in the downward direction. And the weight is going to be balanced by the frictional force, static frictional force, which is going to have N in it. All right, so immediately you notice that the N that you're looking for is located right here. All right, so which means that you have to look at the net force on the y direction. Static frictional force is going to be in the upward direction. Gravity is going to be in the downward direction. And once the person is suspended, there's no acceleration. There is no acceleration once the person is suspended. All right, so this static frictional force is going to be the same as the weight. So static frictional force is this, weight is that. Okay, so let's finish that portion up. It's going to be mu sub s times n. Weight is going to be mg. All right, so sub for n. So n becomes mg divided by n mu sub s. Okay, so that's it. All right, so we'll do a back substitution right here. All right, so when we do a back substitution, what do we get? We end up getting mg divided by mu sub s. And we have rm under the square root. All right, we kind of expected that because n is a reaction force m. So notice that the m gets canceled out of the equation. Conceptually, we kind of expected that. All right, so the mass doesn't matter. Mass doesn't matter. The only thing that matters out of this equation is the coefficient of friction. All right, so for a given radius, it depends on the slipperiest outfit that you can wear. All right, so smaller the coefficient of friction is, the faster you have to spin this. That's what it means. And vice versa. Vice versa. Okay, so that's it. Okay, so lucky for us, we didn't have to do the conversions for the masses. So this is not going to matter. This we need, obviously. So R is going to be 4.57. It's going to be meters. So those of you guys who got a number like that, give yourselves 5 points. Just about every single person did. Okay, so now let's plug the numbers in. So G is going to be roughly about 10. R is 4.57. Mu sub S, what are we using? 0.33. All right, so give me a number. Give me the number.
11.77 meters per second.
11.77 meters per second. All right, give yourself 2 points for that one. All right, this is roughly about what, like 25 miles per hour? 2.24. Which is 26. Okay, roughly about 26 miles per hour. All right, give yourself 5 points for that one. All right, so that worked out. So the mass of the people don't matter. Okay, so next question is why not? All right, guys, the mass doesn't matter. Obviously, it gets canceled out of the equation, but that's not a good enough explanation. When you get to that point, notice that n depends on your mass. Okay, n comes about because your body wants to move in a straight line at a constant speed, right? And wall prevents it from happening. So bigger your mass is, harder you're going to be pressed up against the wall. That's what it means. All right, so n is going to be sensitive to your mass, not your weight, but your mass. Okay, it's sensitive to your body's tendency to want to move in a straight line at a constant speed. All right, so as a result, obviously, masses will cancel out. As a result, the mass is not going to matter, in essence.